Alright, math people, we're here talking about section 3.3, parallel and perpendicular lines. We are on page 6 of your chapter 3 notes. Now this is a short section, so we're going to do it in just one big piece. We're not going to split it up into two parts like the previous ones. We start off with theorem 3.9. You look over the diagram here, you can tell that A and C are parallel to each other because of the arrows, but also B and C are parallel to each other because of the double arrows. Well, this theorem says anytime you have that particular setup, if A is parallel to C and B is parallel to C, the only way that happens is if A and B are also parallel to each other. So we're going to put the word parallel there. And our conclusion is A has to be parallel to B. So our theorem there says if two lines are parallel to the same line, then they must be parallel to each other. Theorem 3.10 builds off of this idea right here. You have M and N, here's a transversal line T, and T happens to be perpendicular to both of those lines. Well, this theorem says if that's the case, the only way that can happen is if M and N are parallel to each other. So you have this particular setup here, and you can now make the conclusion that line M is parallel to line N. And now we're going to take the time to prove that theorem right there. Example 1 says proven theorem 10. If two lines are perpendicular to the same line, then they must be parallel to each other. So we're going to pull the given from the marks you can see on the diagram. We have two sets of perpendicular lines, so we can know that D is perpendicular to line T, and also E is perpendicular to line T. For the prove, you go to the instructions, you pull it off the conclusion, the stuff that comes after the word then they're parallel to each other. So we're trying to show that D is parallel to E. As usual, we'll start off with what's given. Can't use this information until we put it in our proof. So there we go. D is perpendicular to T, E is perpendicular to T, and our reason is it's given to us. Well, if these are perpendicular, then we've created right angles. So we can tell that the measure of angle 1 must be 90, and the measure of angle 2 must be 90. And we could have just as easily put the 1s here and the 2 there. Doesn't really matter. Well, anytime you build off what it means to be perpendicular or anything else, you're using its definition. So our reason for knowing the lines are 90 degrees, the angles are 90 degrees, is that we've used the definition of perpendicular lines, because it's what it means to be perpendicular. Well, if the measures are equal, that means these two angles must be congruent, because that's what it means to be congruent. So we're going to say that 1 is congruent to 2. And we're going to use a theorem here to say all right angles are congruent, because we have a theorem that says exactly that. All right angles are congruent. And you probably could have just said definition of right angles if you wanted to. Well, if you look at our diagram over here, we just showed that 1's equal to 2, and 1 and 2 are a pair of corresponding angles because they're sitting in the same relative location. 1 is in the upper right for this group, angle 2 is in the upper right for that group, so they are corresponding angles. And if we just showed the corresponding angles are equal, the only way that happens if the lines are parallel. So this is going to be our final step. So how did we go from corresponding angles are congruent to knowing the lines are parallel? We used the converse of the corresponding angles postulate. The converse of the corresponding angles postulate. We can't just say corresponding angles postulate there, because that would be going in the wrong direction. If you start off with corresponding angles that are equal, and then you make the conclusion that the lines must be parallel, you're using the converse, not the original postulate. Right, so that takes care of that proof there. We started off by saying that there were two lines that are both perpendicular to the same line, and we ended up by saying that those two lines must be parallel to each other. So we have proven theorem 3.10. Flipping the page. The last two theorems showed that lines were parallel to each other. That was the conclusion, that certain lines were parallel. Now this next one here deals with the conclusion where the lines are perpendicular. So you have a setup here where L and M are already parallel to each other. We know that for sure, and we know that T is perpendicular to line L. Well, the only way that can happen is if T is also perpendicular to line M. So we'll say T has to be perpendicular to line M. And we'll fill in our official blanks here. If a line is perpendicular to one of two parallel lines, then it is also perpendicular to the other. Example 2 here gives you this particular diagram and wants you to prove that C is parallel to B. We'll need to fill in our given, and given we have to pull from the diagram. So over here you can tell that A is parallel to B, so we'll put that. A is parallel to B. You can tell that line T is perpendicular to line A because of the box there, so we'll say T is perpendicular to A, and also T must be perpendicular to C. Well, proof has to come from your instructions. You look up here, it says prove that C is parallel to B, so that's where we're going to put C must be parallel. We're supposed to show that C must be parallel to B. And we're off and running. First off, we'll start off with all the stuff that's given. And sometimes in the book or other places, they will list out the stuff that's given throughout the proof in the order that that information happens to be used. But I like to put it all on step one just to get it out of the way, because you know you're going to use it at some point. So there it is. It's now in our proof. We can use any of those pieces in any order we like. So we're going to use one of the theorems we just learned today. When you look at our lines here, you have T's being perpendicular to A and T's perpendicular to C. The only way that can happen is if A and C are parallel to each other. So that's the conclusion we're going to make here, that A is parallel to C. And our reason is going to be theorem 310. Now on a quiz or test, you're probably not going to remember which one is theorem 310 and which one's not. So we're going to actually sit here and write out the theorem real quick. If two lines are perpendicular to the same line, you can see that set up here, two lines being both perpendicular to the same line, then they are parallel to each other. So here you go, two lines being perpendicular to the same line, then they must be parallel to each other. So that explains how we went from step 1 to step 2. So keep in mind, we're trying to show that C is parallel to B here, and we just showed that B is parallel to A and C is parallel to A. Well, if they're both parallel to A, then B and C have to be parallel to each other. So we're ready to finish this off. This one's only going to take 3 steps. And now we need our justification. We're actually going to use theorem 3.9, but again, we'll write this one out. If two lines are parallel to the same line, then they have to be parallel to each other. If two lines are parallel to the same line, then they are parallel to each other. So we pulled the information given from the symbols in a diagram, built off that idea, and end up by proving that C is parallel to B. So like I said, that was a short section. Basically we had 3 theorems that dealt with parallel and perpendicular lines, and we did a couple proofs regarding those rules or using those rules. And you can tell that next time here we're dealing with parallel lines and the triangle sum theorem. We will talk to you next time.